Hi everyone, welcome back. This is the second video segment for section 5.3 and 5.4. I'll combine those sections into a single sort of presentation series because of the similarities between the two sections. So as you recall, last time we had derived an equation for the cosine of a sum. So we're starting to manipulate the arguments now, and I'm going to switch over here to my document camera, and we will take a look at what we've got going on here. Okay, so again, this is section, I'm going to start labeling these 5.3 and 5.4. This is page 3. Okay, so recall that we came up with this equation that cosine of a sum, and now maybe I'll shift back to Roman letters. So the cosine of a sum is equal to the cosine of the first thing times the cosine of the second thing minus the sine of the first thing times the sine of the second thing. Okay, this is you know, box it, bold, whatever you need to do, because this is one of these formulas that will come up again and again and again. So I thought about this in the intervening time between the last video and this one, that I was going to delay applications until the very end after we proved these 6 different relationships. But I think maybe it's beneficial to do this right now. So we had originally asked about, well, what do you do if you've got, you know, if you look at the angles we know now, we know the exact value for 0 degrees, 30 degrees, 45 degrees, 60 degrees, 90 degrees, and then corresponding angles with the same reference angle in every quadrant. And it should be kind of obvious that there's these missing terms at 15 degrees and 75 degrees that is just begging for us to find their value. And this is actually how we're going to be able to do it. So let's do this. Let's try to find what the cosine of 75 degrees is. Okay? So note first that we can write 75 as a sum. So this is the cosine of 45 degrees plus 30 degrees. Okay, and this is really the key. So now we're going to apply this formula where A is equal to 45 and B is equal to 30. So we'll have the cosine of 45 degrees, right? That's the first term, times the cosine of 30 degrees minus the sine of the first term, which is 45 degrees, times the sine of 30 degrees. And we know all those exact values. So cosine of 45 degrees is square root of 2 over 2. The cosine of 30 degrees is square root of 3 over 2. The sine of 45, square root of 2 over 2. And the sine of 30 degrees is just simply 1/2. Now simplify these. We end up with the square root of 6 over 4 minus the square root of 2 over 4, which I'll combine into a single term, square root of 6 minus square root of 2 over 4. And that may look a little weird because you've probably not seen a lot of things where you've got binomial radicals, but this is as simple as this gets. So we now have an exact expression for the cosine of 75 degrees. And you can verify that on a calculator if you want. You could type out this expression and then compare it to the cosine of 75 degrees. Now, just kind of an insight, and I've mentioned this, it's been quite a while ago, but when you are when you're working with radians, it turns out that, you know, for example, you have pi over 6, right? That's a 30 degree angle. Pi over 4, that's a 45. Pi over 3 is 60, and pi over 2 is 90. And so it's the denominators that kind of clue you into what's going on. Well, if you see a pi over 12 or some multiple of pi over 12, this is the key. This is sort of the clue that this is a something that's either, well, pi over 12 is 15 degrees, so it's going to be one of those oddball angles. They're 15 or 75, or a reference angle that's equivalent. So using this formula directly, we can get cosine of 75. We could use it further and get the cosine of, say, 105, right? We just have to manipulate what values we plug in here. How would we get to 15? Well, it turns out that we didn't really say anything about A and B. Their SIGN could definitely be negative, okay? And so we could think of this as being 45 plus a negative 30 degrees, and we could come up with a value for cosine of 15 degrees. It is, in some sense, that's a little unnatural, and so what we would like to do is we would like to develop a formula where instead of A plus B, we want A minus B, where both A and B are positive numbers. Okay, so that's sort of the first thing I'm going to develop here. And it's a little bit of trickery, but it's basically along that lines. So if you think for a second, so cosine of A minus B, okay, where A and B are both positive angles. If we wanted to figure out what this formula is, then we could rewrite this as the cosine of A plus a negative B. So I'm playing around inside the argument. Notice that this is, I mean, the argument, those are equal to each other. And now I have the formula I had before, where I have an angle plus another angle. Now the SIGN of these angles is irrelevant for the purposes of this formula, but here's what we're going to pull out. So applying the formula, that's going to be equal to the cosine of the first thing, which is A, times the cosine of the second thing, which is minus B, minus the sine of the first thing, which is A, times the sine of the second thing, which is minus B. Okay? So now think back to those symmetry identities and how a negative sign can move in and out of the argument with depending on whether the function is odd or even. Well, cosine is even, and so that negative sign is just going to basically vanish, whereas sine is an odd function, and so that negative sign is going to come out of the expression and transform this leading negative coefficient to a positive. Okay, so I'm going to do that in a couple steps here. The first is that cosine of A times cosine of B, there's the application of that symmetry identity for an even function. And then I have minus sine of A, and I'm going to kind of bracket it off here, minus sine of B. And then I'm going to distribute that negative sign, and I'm left with cosine of A times cosine of B plus sine of A times sine of B. Now, be very careful, because what I've seen more times than I can count is this confusion about how that negative sign works. And so I'm going to give you an example here so that we can kind of apply this. So this is now page 4. Okay, so let's look at one of these. How about the cosine of 15 degrees? Now we can write that as a subtraction. This is the cosine of 45 degrees minus 15. Now we could do this exactly like saying that A is 45 and B is negative 15, but let's apply the negative version of this. So taking A to be 45 and B equal 15, applying the cosine A minus B formula, we have that this is equal to the cosine of the first thing, which is 45 degrees, times the cosine, oh sorry, this should not be 15, made a small mistake there, 30 degrees. Cosine of 30 degrees, and remember the negative version has a change in sign here, so it's plus sine of the first thing times the sine of the second thing. And I keep saying the first thing, second thing, because I want you to move away pretty quickly of A and B and X and all that sort of stuff, but really think of that as whatever the first angle is, whatever the second angle is, because it might have an expression that has variables in it, who knows what. So substituting the values, I'm going to go a little bit quicker because we've already done them. Square root of 2 over 2 times square root of 3 over 2 plus square root of 2 over 2 times 1/2. And notice this comes out to something that looks very similar to the last one. Square root of 6 over 4 plus square root of 2 over 4, which when you combine them is going to give you square root of 6 plus square root of 2 over 4. It turns out for both sine and cosine, for those oddball angles, 15 or 75, you're going to get different combinations of plus or minus square root of 6, plus or minus square root of 2, all over 4 for every one of them. It's not something that I'm going to ask you to memorize these exact values, but you should be able to derive them. Okay, so to summarize then, we can put both of those formulations together. So cosine of A plus or minus B is going to be equal to the cosine of the first angle times the cosine of the second angle, reverse the sign, so minus plus, sine of the first angle times sine of the second angle. Okay, and this is the big picture result for section 5.3, which seems weird that we have a whole section just to prove those groups. Okay, so where do we go from here? Well, it's great that we've got sine, we've got cosine. But what about the other trig functions? We know that in order to be able to extract other trig functions values, we need to either use some of these fundamental identities or maybe create our own formulations. So here's what I'm going to do. I'm going to do another trick. Okay. I'm going to start by trying to say, well, let's try to do this for sine. So sine of a sum, okay? Well, I don't really know a formula for this, but I do know a formula for cosine of a sum. So you may recall that we had the ability previously to transform sine directly into cosine by using a cofunction identity. So remember, the cofunction identity is that this will be cosine of 90 minus whatever's in here. So, or pi over 2, but I'll keep this simple. 90 degrees minus A plus B, right? So this is the complementary angle to this angle. And now, this is where my trickery comes in, is that I'm going to rearrange this here so that I have a first term and a second term. So cosine of 90 degrees minus A, then minus B. Okay? That's I mean, that seems like I didn't do anything all that spectacular, but notice now this is cosine of some angle minus some other angle. And we have a formula for that. It's sitting right there, right? So first angle minus second angle is going to be cosine of the first thing times cosine of the second thing plus sine of the first thing times sine of the second thing. So let's go ahead and write that. So we've got cosine of the first thing, which is 90 degrees minus the angle A, times the cosine of the second thing. Now remember, because we're doing A minus B, the sign will be opposite. So plus sine of the first angle times sine of the second angle. Okay? Now, here's here's a cofunction identity staring you right in the face, and there's another one. So by simply using a cofunction identity, we can transform these into their cofunction. So this first term becomes not cosine of 90 minus a, but actually sine of a. And cosine of b, nothing changes there. Then plus sine of 90 minus a will become cosine of a. Times sine of b. Now, this is not the way that I remembered this when I was first taught this, whoa, these many years ago. I remember this as sine a cosine b plus sine b cosine a, but those are equivalent. Either way that you remember this is fine. Anyways, so like I said, I usually, when I'm writing this is not the most natural for me. So what I will do is simply write it the way I remember it, which is sine of a times cosine of b plus sine of b times cosine of a. And that is the result for sine of a plus b. Okay? I'm going to do, I'm not sure, I think my video is getting a little long here, but what I'm going to do is I'm going to go ahead and flesh out the minus version of sine. I believe this is now page 5. Okay, so we had sine of a plus b. Let's do the same trick we did before with cosine and say, okay, what about sine of a minus b? Well, again, what we're going to do is we're going to write this as sine of the angle A plus the negative angle B. It's a little kind of trick there. And then use our formula, plug in negative B into it, and then use a symmetry identity to manipulate the SIGNs. So first, this is going to be sine of the first angle, which is A, times cosine of the second angle, which is negative B, plus sine of the second angle, which is negative b, times cosine of the first angle, which is a. Symmetry tells you that this is just cosine of b and that this is negative sine of b. So this becomes sine of a times cosine of b plus, and I'll make this substitution, minus sine of b, make it real clear what's happening there, times cosine of a. And now distribute this negative sign. You end up with a formula that is sine of a times cosine of b minus sine of b times cosine of a. Okay, so this is the formula for sine a minus b. Now, I'm going to write these as a group, just like I did with the cosine, so that it's easier to remember a single formula than to remember two of them. So sine of a plus or minus b is equal to sine of the first angle, cosine of the second angle, plus or minus, so whatever the SIGN is here is carried over, sine of the second angle times cosine of the first angle. And that, my friends, is the formula for the sine of a sum or a difference. Big time. This now allows us to find the sine of these other terms. Now you could do that because you can find the cosine, right? You could use a Pythagorean identity to transform sine into cosine or to extract the value of sine, but here we can get it directly, okay? And so I'm gonna go ahead and do a quick example, and I'm gonna do this in radians, and then I'm gonna call this good for this video. So let's do this. Let's find the sine of pi over 12. Okay, now remember that's sine of 15 degrees. So that's kind of the clue, is that it's probably a difference. And you remember what we did before with cosine of 15 degrees was, well, it's 45 minus 30. Anytime you're working with radians, the first thing to do, if it's a 12th, is to break this up into some number of quarters and some number of thirds or sixths. So what I'm going to do is I'm going to write this as sine of 3 pi over 12 minus 2 pi over 12, right? It seems kind of weird, but then I'm going to reduce this down to, I'm going to simplify these fractions, and I end up with sine of pi over 4 minus pi over 6, okay? And those are recall, this is 45 degrees, or equivalent to in radians, and this is 30 degrees, okay? So like I did over previously, and say, well, let's call A equal to pi over 4 and B equal to pi over 6. And it's sine of A minus B. So using the formula, recall that that is the sine of the first thing times the cosine of the second thing. The SIGN will be the same, so minus sine of the second thing times the cosine of the first thing. Okay. Now sine of pi over 4. Well, that's your square root of 2 over 2. Cosine of pi over 6. Well, that's your square root of 3 over 2. Minus sine of 30 degrees, or pi over 6, is 1/2. And cosine of pi over 4, that's square root of 2 over 2, which when you simplify this becomes square root of 6 over 4 minus square root of 2 over 4. And usually you'll see them combined as a single fraction. Square root of 6 minus square root of 2 all over 4. Okay, so like I said, I think my video is getting long. I will come back and do a little bit more here with some of these other, I'll derive the sum and difference formula for tangent, and then maybe we'll look at some identities as well. Okay, thank you.